Hello there, Mr. Sutton bringing you another exponential function lesson, this one on half-life. So we're going to be modeling half-life and other problems that require fractional exponents. Let's begin with the definition. Half-life, which is one of the most common problems we'll see in this lesson, is how long it takes to lose half of something. So for example, the half-life of radium is 1600 years. If 8 kilograms is present now, how much will be present in 900 years? So just getting an intuitive idea for half-life, it takes 1600 years for you to lose half of your radium. So that means after 1600 years, you should have only 4 kilograms left. And we want to know how much there will be in 900 years. Since you haven't gone the whole time period, we would expect there to be more than 4 kilograms. Now let's try this using the standard model to see if we can find out exactly how much is left. So we have f of t equals ab to the t. That's the standard model that we used in the last lesson. And our a value, we're starting with 8 kilograms. The b value, we're multiplying by 0.5. And if we plug those things in, this is what we're faced with. Now, is there something wrong with this? Well, let's test something out. If we plug 900 in for t, we're going to be multiplying by 1/2 900 times. But we don't want to multiply by half even once before we get to 1600. So clearly this is an issue. We want to multiply by 0.5 every 1600 years, not every single year. The solution to this is we're going to use a fractional exponent so that we wait every k years to multiply by whatever this growth factor is. So here's what that looks like as a general formula, and I refer to this as the half-life formula. However, we can use it for more than just half-life, as we'll see later on. But the basic idea is you still have a, you still have your growth factor b, but this time, instead of just having t for an exponent, you have t over k. Let's see how we can use this newer function to help us out with this problem. So we still have our a value of 8. We still have a b value of 0.5. But this time, we're going to have t over 1600 in the exponent. And this is going to force us to wait 1600 years before we get to multiply by the full 0.5. Now, that doesn't mean that, from year 0 to year 1600, you have 8 kilograms the whole time. This thing is decaying constantly. But what it does mean is that if you're plugging in something less than 1600, you're not going to multiply by 0.5. You're going to multiply something a little bit higher so that you're losing less of your original amount. So what are we plugging in exactly? Oh, 900 years. So we'll have 900 over 1600 in the exponent now. And when you're doing this on your calculator, which I'll show you in a sec, on a lot of calculators, you might need to use a parentheses for this fraction here, just for order of operations. So let's check that out now. So here we are. 8 times 0.5 to the 900 over 1600. Again, note that I'm using parentheses here. If I don't do that, then I'm just going to end up raising 0.5 to the 900th power, which is going to give me a really small number, and I'm going to go blissfully divide that by 1600. Not what I want to do. All right, so with the parentheses, I get 5.4 and some change, and this is a reasonable answer. We shouldn't get 4 because it's less than the full 1600 that we're waiting for. Let's do another problem now. A population of rats quadruples every 3 months. If there's 200 to start with, write a formula for f, the population of rats after t months, and then how many rats will there be after 18 months. So pause the video and give it a shot. Let's see what we came up with. So again, we're not multiplying by quadrupling. That's multiplying by 4, right? We're not multiplying by 4 every single month. We want to do this once every 3 months. So this is a good indication that we need our half-life formula if you have to wait a certain time period before using the growth factor. A value, we're starting with 200 rats. Growth factor, quadrupling, again, that's multiplying by 4. And for our k value, we're waiting 3 months before we do that. So this is going to be t over 3. Now we're going to plug in 18 months. So that's going to be 200 times 4 to the 18 over 3, calculator time. And I know we could just write 6 instead of 18 over 3, but I'm being really lazy here. So we come up with 819,000 and 200 rats. For our last problem, we've got this turtle here that starts 50 feet away from a pond. Every 3 hours, it covers half the remaining distance to the pond. How far from the pond will it be in 20 hours? So this is another good half-life problem. Pause the video and give this one a shot. So here's our half-life formula. And we've got an A value of 50, that's our starting amount of feet. B value of half, because we're multiplying by half every single 3 hours. And then K value is going to be 3 hours. And now we want to know at exactly 20 hours what the situation is going to be. So let's plug in 20 to all that. And let's plug that into the calculator. The calculator says about 0.49 and some change. So that's about 0.5 feet. So that's the solution to this problem. Now here's another interesting question. Will this turtle ever actually reach the pond? And the reason I called this Zeno's turtle, there was a Greek philosopher, Zeno, who asked about a turtle in this very situation that kept moving half the distance to some location. And is it ever actually going to reach that destination? What do you think? Well, I mean, my argument for this is you're basically asking when the y value is 0. And we know for exponential functions, there is a horizontal asymptote at y equals 0. Because you can't ever actually get 0 by multiplying a number by itself over and over again, unless the number itself is 0, which it isn't. So our turtle here may be out of luck. All right, we have to do one more problem, just so we can end this lesson on a happy note. We have an investment increasing by 27%, but it's only every 7 years. How much will an initial investment of $3,000 grow to in 40 years? Pause the video and give this one a shot. All right, now most investment interest problems don't really involve half-life, but this one does because of this every 7 years part. So we can use our half-life formula for this. So we have an initial investment of $3,000. That's our A value. We also call that the principal. We'll see that later on. B value, we're increasing by 27%, so that'll be multiplying by 1.27. And we're doing that every 7 years, so that'll be T over 7. We want to know what this is going to grow to in 40 years, so let's plug in 40 for T. And for our calculator answer here, ooh, that's a good amount of money. So we've got $11,756.70. Now that's something to be happy about. So that's all for now. Hope you found this interesting. Until next time, this is Mr. Sutton signing off.